Hello, welcome to the last week of the course Fundamentals of Semiconductor Devices by Professor Gibo and Nath. Hello, welcome to final week of the course Fundamentals of Semiconductor Devices by Professor Gibo and Nath. So, I am Mayank Goyal and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. And this course is being taught by Professor Digvijay Nath, who is an associate professor at IISc Bangalore. The course plan for this week is basics of transistors, different functions like high speed logic, RF, power switching, memories, low noise, next generation, and also micro fabrication, that is how the fabrication is done of these devices. So, like always, I will be giving you practice questions to help you understand this week's topics. So first question: what happens during the off state of a transistor? It conducts high current, it blocks low voltage, it blocks high voltage and allows small leakage current, it operates at maximum power.
Option C is there.
That is correct. It blocks the high voltage and allows small leakage current. Then what defines the on state of a transistor as a switch? It allows no current to flow. It blocks high voltage. It allows high current to flow at low voltage. It generates heat.
Yes, option C, sir.
That is correct. It allows high current to flow at low voltage, which is similar to basically a normal physical switch that you have. There's a off state where you don't have any electricity, and an on state where you have electricity. It's similar to that. Next question: what does the Balega figure of limit relate to? Breakdown voltage and on resistance, input current and output voltage, frequency and gain, efficiency and power. So the answer to this is breakdown voltage and on resistance. So for a power transistor, these are two important metrics: breakdown voltage and on resistance. So what happens when you increase the breakdown voltage according to the Balega figure of merit? The on resistance decreases, the on resistance increases, transistor becomes more efficient, transistor can switch faster.
Sir, on resistance decreases, sir.
That is correct. The on resistance increases. So In the context of transistors, what does it mean to have a low on resistance? The
Sir,
transistor does not conduct electricity. Transistor can carry large current with minimal energy loss. Transistor is inefficient. Transistor has a high breakdown voltage.
sir,
Yes.
previous answer was decreases, na?
Oh.
dV square by R1.
What? Say again.
Sir, actually, uh, your last question,
Yes.
question of 4.
Yeah.
Sir, actually, in case of Baliga figure, the formula is dV square by Rn, R1.
Breakdown voltage increase, your R on is also increasing.
But sir, formula is dV square by R1, na?
Yeah. So if you are increasing your VR, then your I on is also increasing. Just that your figure of merit is constant.
Okay. Figure of merits constant. Okay, sorry.
So what does it mean to have a low on resistance?
Sir, carry large current, minimal energy loss.
That is correct. So you so you you prefer a low on resistance because you want to carry, you want your energy loss to be minimum, and you want your breakdown voltage also to be higher so that you can have a higher power output. So you want to operate at higher voltages, but you also want a low on resistance. But there's a trade off. You cannot have both. When a power switching transistor is rated at 10 ampere and 600 volts, what does this mean? It simultaneously handles 10 amperes at 600 volts. It carries 10 amperes in on state and blocks 600 volts in off state. It requires 600 volts to conduct 10 amperes. It has a constant resistance of 60 ohms.
The maximum current 10 ampere in on state and 600 volt maximum blockage in off state.
That is correct. Ca- it carries 10 amperes in on state and blocks 600 volts in off state. So that means when the transistor is on, you can have a conduction up to 10 amperes, and when it is off, you can go up to 600 volts before breakdown. How does gallium nitride compare to silicon in terms of Baliga figure of merit? Performs worse than silicon, performs exactly the same as silicon, performs better than silicon, cannot be compared to silicon.
The better. Gallium nitride perform better than silicon.
That is correct. Gallium nitride is better than silicon in terms of Baliga figure of merit. But then, what is the major characteristic of silicon in power electronics? It has higher breakdown voltage. It is cheapest and most scalable material. It performs better than gallium nitride. It can switch at very high frequencies.
A-level material. A-level material.
So it is the cheapest and most scalable material that we currently have with decent power switching performance. All other materials with better performance than silicon are not that easy to manufacture. What determines the fundamental limit of the Baliga figure of merit? Manufacturing process, device size, material parameters, operating temperature. So which of these is the
Sir, I
Baliga?
think I think I think the material parameter is not considered, sir.
Why?
Because you say that it is defined on the breakdown voltage and on resistance. If
No,
the
that is what the figure of merit is relating. But how do you come up with the figure of merit? But like what which of these parameters is defining what your figure of merit turns out to be? So the answer to this is material parameters. So the your Valiga figure of merit primarily depends on which material you are using. So if you see in this curve, you will see that this is if you see this is in log and log scale. So it is linear in log b by log VBR by log ion R on. That is the linear relation it is having, and you can see that silicon. So the farther right it is, the better your figure of merit will be. So you see in all these, the silicon is the worst. Then it's your silicon carbide. Then it's your gallium arsenide would be somewhere in between silicon, then gallium arsenide, then it's your silicon carbide, then it's your gallium nitride, then it's your gallium oxide, then here you have aluminum nitride, then diamond, and the highest that predicted figure of merit is for crystalline boron nitride. So if you are able to make a, tran- a transistor out of crystalline boron nitride, not just boron nitride, it has to be crystalline, then you will have the best Baliga figure of merit. It will perform the best power transistor. What is a key application of power switching transistors in solar energy systems? Energy storage, DC to AC conversion, temperature regulation, light absorption.
conversion, sir. This is really conversion.
That is correct. It's for DC to AC conversion. So the the energy that you are getting out from solar cells, the power you are generating, it is in the form of DC current, direct current. But all the appliances in our homes, they run on AC current. So we want to convert first DC to AC, which is done using called oscillators. So there are rectifiers which convert your AC to DC, and there are oscillators which convert from DC to AC. And in those oscillators, you use power switching transistors.
Sir, it is also called inverter, na?
Yeah, inverter is similar. Inverter is a big machine that consists of multiple oscillators. In RF power amplifiers, what is the primary function? Voltage conversion, signal amplification at radio frequencies, DC-DC conversion, current limiting.
Signal amplification and radio frequency.
That is correct. It's in the name itself, RF amplifier. So you want to amplify your RF signal. RF signal is in the gigahertz range, megahertz to gigahertz range signal. You want to amplify it. So that for that you use RF power amplifiers. What does the term transconductance refer to in transistors? Voltage drop across the transistor, relationship between output current and gate voltage, frequency response of the circuit, maximum voltage swing.
output current by gate voltage then.
That is correct. It would be output current with gate voltage. So your output conductance is your drain. So in a transistor, you have two types of current voltage characteristics. One is output characteristics and one is transfer characteristics. So output characteristics is drain current versus drain voltage, and the conductance, if you calculate that, that is called output conductance. And then transfer characteristics is gate current versus, sorry, drain current versus gate voltage. And there, if you calculate the conductance, it is called transconductance. What is the significance of transconductance in RF transistors? It determines the breakdown voltage. It affects the device frequency response and speed. It controls the power consumption. It determines the device size.
Take the device frequency response and speed.
That is correct. It will affect your frequency response and speed. So basically, transconductance, you are calculating at what gate, at what gate voltage, what current you will get, or at what current you will get what gate voltage. So by that, using that, you have to get a optimum current and voltage so that you get your maximum frequency response. What parameter defines the drain efficiency in RF power amplifiers? Input RF power divided by DC power, RF output power divided by DC power, total power loss divided by input power, DC power divided by RF output power.
Is it C? Total power loss by divided input power.
That is correct. It will be RF output power divided by DC power. That is how much DC power you are giving and how much RF output power you are getting. What does power added efficiency means? Total output power divided by input power, RF output power minus RF input power by DC power, DC power divided by RF output power, RF output power times DC power.
B sir.
It will be RF output power minus RF input power by DC power. So basically you are giving some input power, and to amplify the signal you are giving a DC power, and finally you are getting an output power, RF output power. So if it is adding 100, if your power added efficiency is 100%, then all your DC power should be converted to the RF output all your DC power should get converted to your RF power, and your net RF output power should be the RF input power and DC power. So that is, so PAE is defining how much of the DC power is getting converted to your RF power and getting added to your RF input signal. How does the gain of an RF transistor typically drop with frequency? 10 dB per decade, 15 dB per decade, 20 dB per decade, 25 dB per decade. So the answer to this will be 20 dB per decade. That means for every 10 times frequency, your gain is decreasing by 20 decibels. That is, if let's say if your gain is 100 dB for 10 hertz, at 100 hertz your gain will be 80 dB. Then at 1000 hertz your gain will be for 60 dB, like that. What is the Johnson figure of merit primarily used to evaluate? Thermal resistance of RF devices, efficiency of solar cells, performance of RF transistors, storage capacity of memory devices.
Is the performance of RF transistor.
That is correct. It defines your performance of RF transistors. So, like, what happens to speed of an RF device when the breakdown voltage is increased? Speed increases, speed decreases, speed remains constant, speed fluctuates.
Constant.
So the answer is speed decreases. So if you are increasing your breakdown voltage, your speed will decrease. So your performance will be worse. Performance will be bad. Similarly, same it's this similar question. What does the term power frequency trade-off refers to in context of RF transistors? Balance between power consumption and frequency response, trade-off between breakdown voltage and output frequency, operating frequency, correlation between power output and memory storage, efficiency of different transistor materials. So it is given by trade-off between breakdown voltage and operating frequency. So if you have a so you want both your breakdown voltage and your operating system frequency to be higher, but there's a trade-off. If you increase your breakdown voltage, your operating frequency will decrease. If you increase your operating frequency, your breakdown voltage will decrease. So the trade-off is there. So that is called power frequency trade-off. What type of memory does not use transistors? DRAM, magnetic hard drives, flash memory, SRAM.
It's a magnetic hard drive.
That is correct. So in magnetic hard drives, there are no transistors. It is basically using magnets. There are changes in the the typical hard disk drive that you use in a computer. They are basically magnetic disks, and using magnets, their magnetic domains orientations are changed, and that is how you define your ones and zeros in the hard drive. In DRAM, flash memory, SRAM, you use the transistors. So why is flash memory called flash? Due to its bright display, because of its quick charging discharging, due to its power consumption, because of its luminescent properties.
Sir, I think it is quick charging and discharging, sir. Or sir, power consumption out of these two, sir.
It is because it has very fast charging and discharging, so you can charge and discharge it very quickly. That's why it's called flash memory. So in a flash it gets charged, in a flash it gets discharged.
Sir,
Yes.
can I ask you one more question, sir?
Yes.
Sir, I heard that flash memory also being uh, off if somebody is not used it for a certain of time, sir.
What?
So, suppose if one example of flash memory is pen drive. Pen drive is the example of flash memory, sir. Is it?
Yes. So pen drive, your pen drive generally uses a flash pen. The technology in a pen drive is generally used at least in older times it was flash memory. That is why it was also called flash drive.
So, sir, I read that in case of pen drive or any kind of flash memory, if you connect this and you are not operating it, it it will be automatically go to the go to the low power consumption mode.
So no, so
So, so is the option is power consumption is also correct or not?
no,
It
no.
can, it can,
So, but that is not why is that is not why it's called flash. Question
okay,
is
okay.
why the flash term is there.
No, this is one means this is a additional feature is there that it can be if I not use this, it can go to the power saver mode.
No, that is a feature. That is not what is the question. Question is why the term flash is there.
I understand that question. I understand. I just want to ask you that if the feature is available in Flash in case of that type of memory.
There's no as such low power consumption. It's basically just that the typically the power consumption is less. The power to maintain its to so there you need power to maintain states, on state and off state. You need some power to maintain.
Okay,
So that it has low power consumption.
okay, okay, okay.
In a flash memory device, what is the purpose of the floating gate? To increase current flow, to store electric charge, to reduce power consumption, to amplify signals.
And I think it will be stored electric charge, sir, because floating gate is stay above the your conduction. Means it will be beyond your some gap is there, so it can be stored electric charge, sir.
It is correct. It is to store electric charge. In a flash memory, erasing. So let me. So let's say this is your. These are your source and drain. This is your channel. So there will be a oxide layer here. Then you will have your floating gate. Then you will have a very thin oxide. And then you will have your control gate here. So this is called control gate. And this is floating gate. So when you are making connections, so you will have a connection here. You will have a connection here and you will have a connection here. You won't have any connection to your floating gate. So that is why it is called floating gate. So it is at floating potential. You are not defining so at source, drain and control gate you are defining what potential I want to keep them at. But at floating gate there is no connection. So it has a floating potential, that is its potential will be defined by these three. So what happens is when you give us potential to control gate, so the carriers that are generated here, they will tunnel through this very thin tunnel oxide and they will come to the floating gate. So let's say if electrons are generated here, they will come here and they will come to this floating gate, and therefore this floating gate will then get charged and it will create a potential. But when I remove this, when I remove my connection from control gate, then there is no place for these electrons to go out. They are trapped in the floating gate because there's an oxide above it, there's an oxide below it. So this floating gate remains at a potential, and due to this potential there is so it creates a potential across the field effect across the channel. So that is what charging and discharging is called. So it you're charging charging means you are storing electrons in the floating gate, and discharging means you are removing electrons from the floating gate, or you are basically storing charge and removing charge from the floating gate, which is affecting your field effect at the channel. That is how your flash memory works. So next question: in flash memory, erasing operations occur when no voltage is applied, positive voltage applied to control gate, negative voltage is applied to control gate, both gates are grounded. So the answer to this would be when positive voltage is applied to control gate. So we just saw, if you give a negative voltage, you will you will increase the electrons in control gate. These extra electrons will tunnel to the floating gate, and they will then, after removing the after removing charge on the floating gate, these electrons are still trapped in the these electrons are still trapped in the floating gate. They have no way to escape. So your floating gate is charged. That is, you have written something on the floating gate. And so similarly, when you apply a negative, you apply positive voltage here. So electrons will be depleted from the control gate. So electrons, to refill the electrons in the control gate, you will have electrons going back from floating gate to your control gate. And then your floating gate will no longer have any charge. This this is called your erasing. So you are erasing what you had written in your floating gate. So a charge, when floating gate is stored, there's charge stored in the floating gate. It's called 1, and when there's no charge in the floating gate, it's called 0. So you see, so to maintain charge to maintain charge, you don't need to have a voltage applied to your control gate. So that is why it is low power consumption. It will maintain its state even without power, even without wires. The control gate is a flash memory is
Sir,
connected to the.
what you say in last sentence, sir? It can
Yes.
erase without.
So what I am saying is, so you don't need you don't need to give a constant you don't need to give a constant voltage or control gate to have your floating gate charged or discharged. Even if you remove voltage from the control gate, your floating gate will maintain its state. So that is why and to write and to and since there is since there are so even when writing and erasing, you will see that since both control gate and floating gate, they are not carrying any current, so there will be very low current for writing and erasing. So that is why they are low power consumption. They don't need a very high power. So there are basically three components: one is writing, one is erasing, and one is holding. So writing means you are converting from 0 to 1. Erasing means you are converting back from 1 to 0. And holding means you are holding your state. If it's at 1, you are holding it at 1. And if it's at 0, you are holding it at 0. So at each of these states, in flash memory, the power consumption is very less. The control gate in a flash memory is connected to the source, drain, word line, bit line.
It is a drain, sir.
No, the control gate is connected to word line. So there are two types of lines: word line and bit line. So word line is your input and bit line is basically your output. So if you want to write, you write through the word line, and if you want to read, basically you want to read what is written in your memory. There are read and write operations, right? So if you want to write, you write to the word line. If you want to read, you read through the bit line. So the bit line is source flash memory is connected to the control gate, floating gate, drain,
And floating gate,
source.
sir.
Now the bit line is connected to your drain. So when you are writing, you are giving your signal to your word line, and according to the word line, it is changing the potential at the control gate, and accordingly, it is changing the charge at the floating gate. So your floating gate is not connected to anything. So that so it is only being controlled by the control gate. So there and accordingly the how much charge if floating gate has charge or it does not have charge, accordingly your drain current will change, because it will change the gate voltage on a channel. So by checking what the drain current is, get what the you can get what the state of your transistor is, whether it's at 1 or whether it's at 0. So the reading you are doing is through the bit line, which is connected to your drain, and the writing you are doing is through the word line, which is connected to your control gate. What is areal density in memory devices? Number of memory cells per circuit, storage capacity per square inch, Thickness of memory layers, number of transistors per chip.
Sir, is this thickness of memory layer, sir?
No, it is storage capacity per square inch. So that is if on 1 square inch of my wafer, how much amount of storage I have. That is given by my memory areal density. And you want to have highest areal density so that you can pack more and more on on less and less size. So you see in earlier days, if you buy a flash drive, you will get like 512 MB, 1 GB, 2 GB maximum. Nowadays, flash drives come like minimum is like 16 GB, and you can even buy flash drives 512 GB, 1 TB flash drives are also there in the market. So, and your phone, you can see how much space your phone takes, and how much space is the size your memory cell in your phone, how small it is, and it is carrying so much data. So your storage capacity has increased dramatically from earlier. And this is the same type of storage. I'm not even comparing it to your hard disks, which are huge. In terms of areal density, which has been surpassing traditional hard drives, magnetic tapes, SSDs, optical disks, DRAM.
Sir, SSD, sir.
That is correct. So
Solid state device.
I just explained how SSDs are so small compared to traditional hard disks, and they carry same amount of data. What type of memory is primarily used in computers for booting? SSD, flash memory, DRAM, magnetic memory.
DRAM.
That is correct. The answer is DRAM. So when you are booting your computer, a lot of instructions are being written and erased. So a DRAM means dynamic RAM. So it's purposefully made for that purpose, that you can have a large number of writing and erasing operations in small time. There is another type of RAM which is SRAM, which is the type of RAM that is typically used in the in your laptop, your computers. The DDR RAMs, your DDR3, DDR4, DDR5 RAMs that you install, they are typically SRAMs, static RAMs. What does CMOS stand for? Complementary metal oxide semiconductor, conductive metal oxide semiconductor, composite metal oxide semiconductor, composite multi-layer oxide semiconductor.
Complementary metal semiconductor.
That is correct. The answer is complementary metal oxide semiconductor. So basically, it means that you are making MOS caps and MOSFETs, both P type and N type, on the same wafer. So therefore, the term complementary is there, because the same process is being used to make both P type and N type MOSFETs. So it's complementary between the two. Which process is commonly used for fabricating silicon dioxide gate dielectrics? Diffusion, thermal oxidation, ion implantation, etching.
Sir, is it ion implementation? Uh,
No, the answer will be thermal oxidation. What is the purpose of photolithography in semiconductor fabrication? To deposit metals, to remove excess materials, to transfer patterns onto the silicon substrate, to oxidize silicon.
to remove excess metals.
To transfer patterns onto the silicon substrate. So basically, if you want to make some pattern devices, pattern deposition or pattern etching or pattern something on your on your wafer, so use photolithography to create those patterns.
Example, sir, please.
So example basically is like if I'm making my let's so like I saw told you. So this is how source drain is made. So like n plus, and this is your p region. So you want your anions to deposit here and here, but you don't want here. So you make a blocking layer here. So this is a blocking layer. What it does, it does not allow your ions to reach the wafer here. So you see the blocking layer that we have formed is patterned. It's only in this region. It's not in. So it's not. Let's say like this. It's a big wafer. So here will so it will be your blocking layer here everywhere. Only in this regions you don't have your blocking layer. So to make that part, you do photolithography. So if let's say you first deposited your blocking layer, then you do photolithography so that in the blocking layer these regions are exposed. And then you when you etch it, then blocking layer here and here will get etched. Blocking layer other areas will be there. And when you do your doping, so it will only affect these regions. It won't affect these regions which are covered by our blocking layer. And this is just one of the many purposes of photolithography, of patterning your substrate. There are many reasons. So when you are depositing your metal, then also you need photolithography. When you are doing some etching, when you are doing some doping, when you are doing oxidation, all those all those places where you need a pattern, where you don't want to your whole wafer to get converted, that places you want photolithography. What technology is used to improve the control of short channel effects in transistors? Planar CMOS, FinFET, BJT, SRAM.
FinFET, sir. FinFET.
That is correct, FinFET. So FinFET basically there's a much higher gate control and much higher carrier confinement compared to normal CMOS. In a FinFET, it looks like this. So you see so this is your channel, and the source drain are connected to the edges of it, and this is your gate oxide. This is your gate oxide. So there's a much larger overlap of your gate oxide in FinFETs compared to your normal planar CMOS. So that and your channel also becomes smaller. So that increases your carrier confinement in the channel and the gate control. How
Sir,
much silicon is what?
in case of sir FinFET, number of gates are two.
It is considered one gate only because it is convert it is the channel that is being counted, not the gate.
So, sir, is there any devices there which are three side gate is there?
What?
Means it has three gates are there. GAA. Is there
GA
any means
GAA is
functional
gate or
device?
all around. In
Means
what in GA what happens is, so it is like this. GA is gate all around. So this is your gate oxide and this is your channel. These are your channels. So you see the channel is all converted all around from your gate.
Okay, okay. Sir, this is means much effective than your FinFET.
Yes.
Is GA is more input technology compared to your FinFET.
Yeah, GA is better than FinFET. FinFET is better than planar CMOS and GA is even better than FinFET because of because the gate control is even higher in GA. How much silicon is consumed to grow 100 nanometer of silicon oxide dioxide? 100 nanometer, 22 nanometer, 44 nanometer, 88 nanometer. So you can find the answer to this.
Sir, 100 nanometer.
So 100 nanometer silicon dioxide, how much of silicon will you have to give to get 100 nanometer silicon dioxide? So the answer to this would be 44 nanometers. So a general thumb of rule is like one silicon is equal to 2.3 SiO2. So if 1 nanometer of silicon is consumed, you will have 2.3 nanometer of SiO2. So if you see here, 40, to get 100 nanometers of SiO2, you will have to do 100 by 2.3, which is 44 nanometer. And if you want to get what will be the final height of your SiO2, then that would be 100 minus 44, which would be 56. So your SiO2 will be 56 nanometer above your wafer level. Basically, if this was your wafer, what happened now is, and only this much region was getting oxidized. So what will happen now is much region will become SiO2. So it consumed 44 nanometer of silicon in this region and became 100 nanometer SiO2. And from and you will see that this step is now 56 nanometers. From unconsumed silicon to SiO2, it's now 56 nanometers. So that is can also be a question. What is the primary difference between wet and dry oxidation? Wet oxidation is used to get thinner oxides, dry for thicker. Dry oxidation is to get thinner oxides, wet for thicker. Wet oxidation occurs at room temperature. Dry oxidation requires no gas flow.
Sir,
Yes.
sir, in last part you told that 2.3 SiO2 required for one silicon. So if I divide 100 by 2.3, it will be 44.
Yes.
Answer, answer. If I uh, put a layer of SiO2 of 100 nanometer, then 44 will be converted to silicon
No, 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 no.
and remix.
So what in oxidation, what happens is you are converting your silicon to silicon dioxide. You are not depositing silicon dioxide. You are converting silicon to silicon dioxide.
Okay,
So what happens is so you for if you are converting 44 nanometer of silicon to silicon dioxide, you will get 100 nanometer of silicon dioxide.
okay. Then 56 nanometer will be silicon dioxide.
Silicon dioxide will be 100 nanometers. 56 nanometers will be the height of silicon dioxide from your unconsumed silicon.
Okay, okay, sir. Okay.
So the 44 nanometers, so there will be a 44 nanometers dip in your silicon from where your silicon dioxide will be growing.
Okay, okay, sir.
What is the primary difference between wet and dry oxidation?
The dry is the thicker.
So dry oxidation is used for thinner oxides and wet oxidation is used for thicker oxides. So the difference between dry and wet is that in dry oxidation you use oxygen gas and in wet oxidation you use water vapors. So if you are reacting silicon with oxygen in one case and in another case you are reacting silicon with H2O. So the silicon to silicon reaction between silicon and H2O is much faster compared to silicon with O2. So the conversion rate in wet oxidation is much faster. So in the same time, in dry oxidation, if you are growing 10 nanometers oxygen, in wet oxidation, in the same time, you will be able to grow, let's say, 200, 300 nanometers. These are not these are not exact numbers, but I am just giving an idea how fast wet oxidation is compared to dry oxidation. It can be even faster. So, but the problem with that is that the faster you go, the lesser the control on thicknesses. So let's say I want to grow 10 nanometer using wet oxidation and it is being grown in like let's say 2-3 minutes only, then then it is very difficult for me to stop it exactly at 10 nanometers. Whereas if it is taking 2 hours, then I can know if I can know I if I go, let's say, one or two above or below, it will still be approximately 10 nanometers. It won't be like 5 nanometers or 20 nanometers. What is the main advantage of ion implantation over diffusion? Lower cost, higher operating temperature, precise control of dopant depth and concentration, no crystal damage.
And it is precise control of dopant depth and concentration.
So the answer to precise control of dopant depth and concentration. So ion implantation and diffusion are methods of doping. If you so you want to dope your wafer, two methods are it, doping and ion implantation, diffusion and ion implantation. In diffusion, basically you keep your wafer in a environment of dopants, and those dopants then sit on your surface and diffuse into your wafer at high temperatures. So they diffuse into your wafer through the surface and the concentration gradient in the environment defines the how how your how your dopant profile will be in your how many dopants will enter your will sit on your surface and how many will go inside and what your doping profile will be. That is given by your environment dopants in the environment and your temperature and the time. In ion implantation, what you do is you bombard your wafer with high energy ions and they go deep inside your wafers. So what happens is so your your dopants your depth will be determined by the energy of the dopants. So in diffusion your doping will always be maximum at the surface and decrease as you go inside your substrate. In ion implantation the doping will be maximum at some depth inside the your surface, and there will be a very small dopant profile. Most of the doping will be concentrated at that particular depth. There will be very small profile that will deviate from that depth. So you have a very precise control of how many dopants at what depth you want your doping and what concentration of dopants you want. Why is post implantation annealing necessary? To reduce oxide thickness, to activate dopants and repair crystal damage, to improve metal contacts, to reduce wafer thickness.
And B.
That is correct, to activate dopants and repair crystal damage. So when you are doing ion implantation, you are bombarding ions that are going inside your wafer, but they are, but for them to act as dopants, you need them to be part of your crystal lattice. So for that, annealing is done. What annealing does is it it replaces silicon with the dopant near it. So dopant becomes part of our crystal lattice. And if there are any broken bonds that are caused due to the high energy dopants, that get fixed, so it repairs whatever damage was done during implantation, and it also activates dopants by making them part of the crystal lattice. But one negative point of annealing is also this, that it will create a diffusion process within the wafer, so your dopant profile will broaden out.
Sir,
Yes.
tell me one more time, sir. What is the disadvantage of annealing is?
Yeah, so this is your wafer. I am bombarding my ions here. What they will do is they will go and sit in this region, let's say, and let's say you will get a profile like this. But what happens actually is they are not they just go through your crystal lattice and sit here. Here is the point where they lose all their energy. So they start when they start enter your substrate, they start losing energy, and by the time they reach here, they lose all their energy. But like let's say if this is your lattice, what will happen is they let's say they come and sit here. The dopant comes and sit here, and it also breaks this bond. So your lattice is also damaged, and your dopant is not part of your lattice. So your lattice is still acting like there is no dopants there. So when you do annealing, what happens is it will go and replace one of the lattice points like this, and it will also repair any broken bonds or something like that. So now this dopant is part of your lattice, and hence it will act like you have doped it with boron or phosphorus or whatever. But what will also happen is that it will create a bigger dopant region, and like let's say the profile will now look like this, the doping profile. Earlier the doping profile was looking like this. Now it has broadened out. The dopants have spread because of diffusion. So for diffusion you need higher temperatures, which you are providing by annealing. Ion implantation is generally done at low room temperatures, and then annealing is done to fix the damage and to activate dopants, but that also creates a bit of uh, doping diffusion. That is why mostly post implantation annealing is done by RTP, rapid thermal processing. That is it increases the temperature at very fast rate and decreases at very fast rate, so that there is not enough time for diffusion to take place. What are the two main categories of dope deposition processes in semiconductor fabrication? Thermal and chemical deposition, physical vapor and chemical vapor deposition, sputtering and evaporation only, wet and dry deposition.
The physical vapor and chemical vapor dependence. CVD.
That is correct. PVD and CVD. Which of the following best describes physical vapor deposition? Process that uses chemical reactions to deposit materials. Process that produces vapor through heating or ion bombardment. Process that only works with dielectric materials. Process that requires high pressure environments.
The, the
Yes,
B. Vapor through heating and
that is correct. A process that produces vapors through heating or ion bombardment. So you have your material which you want to deposit, and by heating it in vacuum, you can you can melt that material and create vapors, which then go and deposit, which can go and sit on your substrate. In another case, you can bombard it with ions to remove material from your substrate, sorry, your from your desired from a desired material. You remove material which which vaporizes and goes and sit on your substrate. That is called physical vapor deposition. And in CVD, chemical vapor deposition, so you do chemical reaction. So you have two or three materials. You do reaction between them to get a final product. What is the main advantage of sputtering over evaporation? Lower cost, higher deposition rates, better step coverage, lower temperature requirements.
deposition.
So the answer is better step coverage. So the sputtering is where you are creating a, so there are, both of them are methods of physical vapor deposition. So in evaporation, what happens is you have a chamber, and on top your substrate is there, and on the bottom your material is there. What happens is when your material is vaporizing, it is going straight above because of vacuum. There is no, so because of vacuum there is no what drift diffusion in the environment. There is no dispersion. Your vapor, your particles are going straight and sitting on your substrate. Whereas in sputter, what happens is, so there's an ion gun. What it does, it hits your wafer, wave, it hits your target material with ions which create particles, material particles, and a plasma is created in this region. So these material particles, although they are still in vacuum, but due to plasma, they are in random position. So they are coming to your material from all positions, not just straight up. They are coming from all positions because of the plasma, and because of that they are depositing from all regions. So let's say if I have this here, this type of step in my wafer. So for in evaporation, what will happen is it will only deposit line of sight. That is, it will only deposit on the top. It won't deposit on the side. So the step will not get covered. But if in case of sputter, what will happen is it will, since it's coming from all directions, it will although most of it is still coming straight up, but there is also coming from the side, which will come and sit on the side walls. So this side walls coverage is also there in sputter. So that is the main difference between evaporation and sputter deposition. Although all other, so higher deposition rates is also a advantage of sputter. Lower temperature requirements is also an advantage of sputter, because since sputter requires ion bombardment, whereas in evaporation you need to give high temperature to your for a material to melt, like above 1000 degrees, 12,000, 13, sorry, 1200, 1300 degrees. You want to give the melt to the material, whereas to remove material here you just need to fire ions, so the temperature requirement is lesser, and here the deposition rates are also typically higher in sputter. Cost, generally evaporation is cheaper, I think. It's a much simpler, so it should be, cost wise evaporation should be lesser than sputter. What is the correct sequence of steps in CVD? Reaction, adsorption, transport, removal, transport, reaction, removal, adsorption, transport, adsorption, reaction, removal, adsorption, transport, removal, reaction.
See, sir.
No, the answer to this would be C. Transport, adsorption, reaction, removal. So,
What is CBD, sir?
yes, so CVD, let's say I have this tube, my wafer is sitting here, and I have two precursors here. So what will happen is I will, and these are heated. So these are, there's a furnace here. So these dots that I am creating, they are denoting a furnace. And there may be a furnace here also. So what happens is, so you give a carrier, you give a gas here, and what that will do is that will take vapors of these materials, these both materials, to your wafer here. So these materials will come and sit on your wafers. They will come and sit on your wafers. So they will get adsorbed on the surface of our wafer, and then there will be a chemical reaction happening between the molecules of these two materials, and they might also do a chemical reaction with the surface of our wafer. So that will create, this chemical reaction will create a, your desired layer, whatever you want to deposit, and some byproducts. So that byproducts will then be removed by the same carrier gas. This is the carrier gas you are giving, same carrier gas. So first this is transport, then there's adsorption on the surface, then there's reaction between the reactants, and then there's removal of byproducts. So this is the sequence of steps followed in a CVD. So it's called chemical vapor deposition because you are bringing the vapors of chemicals here.
Okay, sir.
What is reactive ion etching? A purely chemical etching process, a combination of physical and chemical etching, a type of wet etching, a purely physical etching process. So this question, I think I have skipped the basic multiple points before this question. First, I should explain what chemical etching, physical etching, wet etching is. So the answer to this is a combination of physical and chemical etching. So so now so now you are reading about deposition. Deposition is when you want to add some material to your wafer. Now you already have some material on a wafer and you want to remove that material. So that process is called etching. And there are, in terms of the material used, there are two types of etching: chemical etching and physical etching. So let's say this is my wafer with silicon and then silicon oxide here, and I want to remove silicon oxide. I want to remove silicon from this region. I don't want to remove silicon oxide. So what I can do is I can so and so and based on the environment, there are two types of etching: wet etching and dry etching. In wet etching, what I will do is I will put my wafer in a silicon etchant solution. So I will have a solution of some acid or some base which only etches, which is selective. It etches silicon, it does not etch silicon oxide. So it will be it will be kept in that environment, that liquid, that solution, and that will come and attack this region. It will also, it won't be able to attack silicon dioxide because it does not react with silicon dioxide. It will come and it will etch this region. And what will happen is it is an isotropic etch. Basically, it will etch from all sides. And in dry etching, what will happen is instead of a solution, I will I will bring in a gas that etches silicon, but not silicon oxide. So that is dry etching. Instead of solution, there is gas. And in physical etching, what will happen is, let's say silicon and SiO2. In physical etching, what happens is I bring in, let's say, ions of a very high energy. I bring in ions, plasma ions of, let's say, argon on some heavy material. What that will do is they will come and hit your wafer and they will take away particles. So they will take away particles from everywhere, but they will only take particles in a particular direction. So it is very anisotropic. It is an anisotropic material. It will only act in one direction. It won't, like, it will only take particles horizontally. It won't take much particles vertically, but it will affect all materials, both silicon and silicon oxide. So there is no selectivity. So what you want is a combination of all these. So you also want selectivity, and you also want isotropy. So for that you use reactive ion etching. What reactive ion etching does is, so it so you bring in a gas of ions which are reactive with silicon. So bring in a gas of ions which are reactive with silicon. Sorry, you want anisotropy. You don't want isotropic etch, you want anisotropic etch, but you want selectivity also. So what you do is you bring in a stream of ions, reactive ions, that will only come in one direction, and they will only etch silicon. They won't affect silicon oxide. So that is called reactive ion etching. So it's a combination of chemical etch and a physical etch. What is the relation between wavelength of light used in lithography and the minimum feature size? Shorter wavelengths allow for larger features. Shorter wavelengths allow for smaller features. Wavelength does not affect feature size. Longer wavelengths allow for smaller features. So the
So what is lithography?
answer to this will be shorter wavelengths allow for smaller features. So in lithography, you are you are shining light on. So what happens is, on your wafer you coat a resist, something called a resist. That is that that becomes soften or harden depending on the light you are giving. So let's say I have positive resist, and then you use a mask. Above that you use a mask which have shaded regions and expo- exposed regions like this, and then you shine light over the whole area. You shine light. So what happens is, so the blocked region, they are they block the light, but the exposed region, they let the light go to your they expose your resist here, and this region then undergoes some chemical changes and becomes softened. Then there is next step is called development, where what will happen is, this softened regions will get removed and only the unexposed regions will remain on the resist. And after that, you do your etching, deposition, whatever you want to do. That will only affect this part of your wafer. And after that you can do lift off, in which resist strip, in which case you remove this resist. So now let's say, now you will only have your wafer like this. So what then? Your minimum feature size means the size of this feature. So a resolution is given by wavelength. So resolution is like 1.22 times wavelength. Lambda by Na, which is numerical aperture. This is resolution 1.22 lambda by Na. So resolution means how much is the gap between two, what is the minimum gap that you can, so that these you have two distinguished regions, and if you get a smaller gap, you will have a region like this where you won't be able to distinguish between the two. So if you use a smaller, so then what this will do is this will bring your features, this will do a feature like this, and what this will do is this will do a feature like this. So this will combine your feature, and here your feature stays separate. So to have smaller features, your R should be smaller, and for R to be smaller, your lambda should be smaller. So shorter wavelength will give us smaller features.
Okay, sir.
So this is actually a very complicated. So VLSI, this fabrication. This is a very broad topic, so it requires a lot of time to explain and understand. So I will probably take a extra class on Wednesday, this Wednesday. I think I will explain VSLI this fabrication in much more detail there, or I can maybe summarize the whole course, help you understand the assignment questions that from previous weeks. Up to you. What if you want to attend and what you want to discuss?
Sir, one question on another question which I want to say is being sir, on another question I want to know, sir.
Yes,
This is why and when does uh, electron and hole
yes.
not lie in the easy level?
What?
Uh, why and when does the electron and holes not lie in the easy cell? Elect, uh, energy get band gap, sir.
I am not able to understand what you are saying. Can you write in the chat?
Sir,
Yes.
uh, Sanjeev say that why electron and holes are not lie in the band gap region. Why and when, sir?
Acha, you are saying why there are no electrons and holes in the band gap region.
Yes, sir. Yes, sir.
Okay. Let's do it here. Let's say. So what actually happens is, so when you're so what happens is when your, let's say, particles are far away from each other, they have a continuous band, but when they get close to each other, their electrons and holes repel each other. So this is a continuous band. So there's everything here. Electrons are also here, your holes are also here. But that is when particles are very far away from each other. When they come close to form a crystal lattice, what happens is these electrons and holes from one particle, they are facing facing repulsion, attraction and repulsion from electrons and holes from the other particles. So what happens is as they come close, your band divides like this. So and you will have two, now you will get two separate bands. So this is at A, lattice constant value, and this is at infinity. When your particle atoms are very far away, that is at infinity, you have a continuous band. There is no band gap there, but but due to this repulsion and attraction of between electrons and holes, you get a band separation. So you have then your conduction band and your valence band. Then you get a conduction band and a valence band. This is energy, and then therefore you get a forbidden region. So this is a forbidden region. There are no density of states here is zero. So if I calculate density of states, then the density of states in this region is zero. So if you by Fermi rule, there should be there is probability of electrons and holes there, but if you calculate density of states, the density of states here is zero. There are no energy states available here. Therefore, you can't have any electron and hole here.
Oh, yes, sir. Yes, sir. Thank you, sir.
Thank you.
This is last class, sir.
This is last class, but I have applied for an extra session on Wednesday. I
Okay.
don't know if there will be the session or not. If there will be a session on Wednesday, you will get the email.
And sir, in that session, you can recap the whole thing, na?
What?
In that session, you particularly recap the old concept.
Uh, Not only on Wednesday. Only they have only offered till Wednesday, so I have applied for Wednesday.
In that class, your content will be
That I told that I can go deep into fabrication, or I can do assignment questions that are already given answers, or I can do a summary of the course.
okay. Okay, sir. Okay. Thank you, sir. Good night, sir.
Good night.